Okay, in this video we're going to briefly explore adding stress to a system and how that system is going to, or adding stress to a system at equilibrium and then predicting how that system is going to react. And this involves Le Chatelier's principle, which states that when a system at equilibrium is stressed, it's going to react in a way to get back to equilibrium and ease that stress. So one way we can add stress is by changing the concentration of any of our reactants or our products. So if we increase the concentration of A, it's going to cause a shift to the right. Whenever we're adding something, the shift is going to be away from whatever it is that we're adding, because we need to make more reactants in this case to balance out the equation once again. I can also take things away. If I decrease the concentration of B, that's also going to shift the reaction to the right, because now I need to make more B in order to compensate. So if I remove something, the reaction is going to shift in the direction of whatever I'm removing. The other thing that I have going on in this equation is heat, and I have the heat on the reactant side, so it means that it's an endothermic reaction. So if I increase the temperature of this reaction, I'm adding heat to the reactant side. So once again, my reaction is going to shift to the right. It's going to shift away from what I'm adding. If I decrease my temperature, my reaction is going to shift to the left, because my reaction is going to shift towards what I'm removing to be able to make more of it. If I increase the pressure on this system, it's going to create more collisions between molecules. So in order to compensate and get back to equilibrium, the system is going to want to shift in the direction that's going to produce the fewest amount of moles. So on my reactant side, I only have 1 mole of A. Over on my product side, I actually have 1 mole of B and 1 mole of C, so for a total of 2 moles. So if I increase the pressure, my reaction is going to shift in the direction that produces the fewest amount of moles. So it's going to shift towards the left. If I increase my volume, increasing my volume is actually going to decrease my pressure, because now my molecules have more space, so they're going to collide less. So when I have an increase in volume, which causes a decrease in pressure and fewer collisions, the system is going to want to move in the direction that creates more collisions. So it's going to want to move in the direction that produces more moles. And finally, if I add a catalyst, this is going to have no effect on my reaction, in that it's not going to cause a shift in either direction, because a catalyst is simply going to increase the rate of both reactions equally. So the other thing I can predict using these different stresses on a system at equilibrium in a closed container is how my Kc or my Keq, my equilibrium constant, is going to be affected, whether it's going to increase, decrease, or stay the same. So, however, the only thing that's going to affect my equilibrium is going to be temperature. So right here. These are the only two things that are going to affect my equilibrium constant. So if I increase my concentration of A or decrease my concentration of B, my equilibrium constant is going to stay the same. However, if I increase my temperature, so having heat over here, remember we said it's an endothermic reaction, and Kc or Keq is equal to the concentration of my products over the concentration of my reactants. And keeping that in mind is going to come in handy in just a second. So if I increase the temperature, I'm going to shift my reaction to the right. So I'm actually going to create more products. So my products are going to increase. So I can kind of plug in some numbers to see what this looks like. So I always like to start with 1 over 2. So 1 for my products, 2 for my reactants. And if I've increased my temperature, I've added heat, and I've shifted the equation to the right, my products are going to increase and my reactants are going to stay the same. So let's go to 2 over 2, 3 over 2, 4 over 2. So my KEQ value is actually 0.5. That's 1, 1.5, 2. My KEQ value is actually increasing. On the other hand, if I decrease my temperature, let's see what happens. So if I decrease my temperature, I'm taking away heat, so my reaction is going to shift back to the left. So I'm going to be creating more reactants. So this time, I'm going to start with 1 over 2 again. Again, 1 for my products, 2 for my reactants. So this time, my products are going to stay the same, but my reactants are going to increase. 1/3, 1/4, 1/5. So as you can see, my KEQ, or my KC, my equilibrium constant, is actually decreasing. So in order to figure out what effect the temperature is going to have on our equilibrium constant, you can plug in some numbers and see, depending on whether it's an exothermic or an endothermic reaction, and which way the reaction is going to shift in response to either an addition of heat, an increase in temperature, or a removal of heat, a decrease in temperature. So this is how you can figure that out, to predict which way our equation is going to shift and what effect that's going to have on our equilibrium constant. And don't forget temperature, so I can fill these in. Temperature is going to be the only factor that's going to cause a change in our equilibrium constant.